Hello friends, today we are going to discuss Fermat's theorem and Chinese remainder theorem. So before that I would like to discuss the theory of the congruences, and these are already explained in the divisibility, but one more time I would like to, all these 6-7 uh, rules are there which you must know. So the rule 1 is quite obvious. You can see that the A congruent A modulo n. And if second one is A congruent B modulo n, the remainder which you get from A and B after division with n, the same thing we have just interchanged. So B is quite obvious, second is quite obvious. Third one you can see that the A congruent B modulo n, B congruent C modulo n, then A congruent C modulo n. For the fourth one is A congruent B modulo n and C congruent D modulo n, then we can write A plus C congruent B plus D modulo n, and A into C congruent B into D modulo n. And similarly, if the fifth one is given that the A congruent B modulo n, then we can add C in both the sides there, and we can multiply C both the sides, and the same this we can write A plus C congruent B plus C modulo n and A C congruent B D modulo n. Similarly, if I keep this in this one, if I keep that C and D are again both A and C, so we get A square congruent B square modulo n, or same thing we can repeat k number of times. So obviously A congruent B modulo n, then A raised to the power k congruent B raised to the power k modulo n. And the seventh one is if CA congruent CB modulo n, and then we can write A congruent B modulo n by D, where D is a GCD of this C and n. So few of the examples I will tell you how we can utilize in our problems. So let's say I take a problem that 3 raised to the power 18's divisibility we have to check by 29. So see, we can write that 3 raised to the power 3 congruent minus 2 modulo 29. 3 raised to the power 3 is 27 divided by 29, then we get the minus 2 remainder. Okay. And then we just using the property number 6, you can write 3 raised to the power 3 raised to the power 6 minus 2 raised to the power 6 modulo 29. So minus 2 raised to the power 6 will become 30 to 64. So 64's divisibility we can check by 29. So when 64 is divided by 29, we'll get 58 and then 2, that is 6 modulo 29. So we can see that 3 raised to the power 18 when divided by 29, we get the remainder 6, and it's not divisible by 29. So I hope it is clear to you. One more example I take. Let's say 2 raised to the power 20 minus 1. Let's say this divisibility we have to check by 41. So we can write 2 raised to the power 5, which is 32, congruent minus 9 mod 41. And further, again using the property 6, you can write 2 raised to the power 5 raised to the power 4 congruent minus 9 raised to the power 4 modulo 41. So this minus 9 raised to the power 4 will become 81's square. So first I will check the this divisibility of 81 by 41. So we can write 81 congruent, that is 82 minus 1 mod 41, and 81's square will become minus 1 square modulo 41, which is 1. So you see the remainder you are getting 1 there. So if I subtract 1 minus, if I 1 minus 1, that is 0. So in that case, if I talk about the divisibility of 2 raised to the power 20 minus 1, so the number is divisible by 41. one more example I'll take for this one. Let's say for the 33 congruent 15 modulo 9. So when 33 is divided by 9, that the remainder you understand that you'll get 15 there. So further what we can do there, 33 can be written as a 3 into 11 congruent, and this is 3 into 5 modulo 9. Now see the seventh property, if CA congruent CB modulo n, then A congruent B modulo n by D. Clear? So D is the GCD of C and n. So you can see that the C becomes 3 there. Clear? And n is a 9. So GCD of 3 and 9. 3 and 9 GCD is 1. Sorry, 3. So we can write that the 11 congruent is A congruent B modulo n by D. So 11 congruent 5 modulo 9 upon 3, that is 3. So after rules of congruences, we have one Chinese remainder theorem which is quite helpful in our Olympiad problems. This theorem says that if n1, n2, nr be the positive integers and such that the GCD of ni and nj is 1, and where I is not equals to j, means these all the n1, n2, these all are co-prime. Then the system of congruences, that is x congruent a1 modulo n1, x congruent a2 modulo n2, and similarly x congruent ar modulo nr, has a simultaneous solution which is unique modulo the integer n1, n2 dot into dot dot nr. So it's very easy to understand this thing. Now first what I'll do, I'll make this, let's say I assume this number is n. So our n is n1 into n2 dot 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 nr. Now I form a capital NK there, which is capital NK is basically n divided by small nk. So n divided by small nk means we have all the from n1, n2 dot dot dot, we have nk minus 1, then we'll have nk plus 1, but we don't have nk there, and finally you have nr. Now in order to satisfy this system of congruences, we must have an equation nkx congruent 1 modulo nk. If I write k equals to 1, we will be dealing the equation number 1. If I write k is equals to 2, we will be dealing the equation number 2. And finally, if I write k equals to r, we will be dealing the final equation. Now see, in order to satisfy this equation that n capital nkx congruent 1 modulo nk small nk, this x, if I write a1 n1 x1 plus, means it has to be like that, ar nr xr. So that way we can, those part of the x1, x2 and xr, we can find it out, and that will obviously become the solution of this equation. Now you see, we also see that the ni congruent 0 nk. So we are not bothered about the rest of the things because that has to be 0 over there. So once we get the x value, that x value is basically a1 n1 into x1 plus a2 n2 into x2 dot 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 ar nr equals to xr. So that will be our x value which will satisfy this equation. And we can take an example also in order to have a better understanding of this theorem. let's say I take equation x congruent to modulo 3, x congruent 3 modulo 5, x congruent 2 modulo 7. This is a system of equation there. So what we can do here, first we'll find what is the n are there. So small n you can see is 3 into 5 into 7. And if you see the capital N1, the capital N1 will be 35. Capital N2 you can see that you will get 21, and capital N3's value will be 50. So if I get the x there, so what is our x will be? So x, that is, first I'll find that find that x1, x2 and x3. So you can see that the equation which I spoke to, that nk x congruent 1 mod nk. So the first equation you can see there, so the nk means the n1 will get 35. So we can write 35x congruent 1 mod and nk, just 3 there. So you can see the x1 value will become 2 there, right? And for the next equation we can see that the n2 is 21 there. So the next equation is 21x congruent 1 mod 5. So you can see x2 is equals to 1 there. And the third equation we can form there. So that equation will be, third equation, that is n3 is 15, that is 15x congruent 1 mod 7. So you can see 14, so that x3 will be 1 there. So now we can get the value of x there. So I'll write here. So you can see the value of x there is a1. So that a1 you can see there, it's 2. So that is a1 n1 x1 plus a2 n2 x2 plus a3 n3 x3. So the a1 is 2 there, so 2 into n1, n1 is your 35, x1 you got 2 there, plus a2 value is 3 there, n2 is your 21, and then you get the x2 value is 1, plus a3 is 2, n3 is 15, and x3's value is 1. So if we simplify this thing, we will get 15 to the 30, and then we'll get 63 and 70, 140. So 140 plus 63 plus 15 is 30. So this will become 233. So now 233, and now your n1, n2, n3. So you can see that the n1, n2, n3 is your this 105. So now if I see that 233 congruent, so 105, it is 210, so that is 23 modulo 105. So this is what our Chinese remainder theorem is there, and I'll tell you in the coming lectures, even in the next lecture I will tell you how to use this important concept in our problems.